what have we done last time? We defined Turing machines. What they are, it's a tape with a head and a list of rules, internal states, and the rules are very well specified. They're a function of what the head is currently scanning and also of the internal state. And we saw that it carries a precise computation that may or may not halt. If it halts, there's an output string, and we say that it has some functionality, that given the input string, it has produced the output string. We actually come back to that today. But more importantly, I finished with reading bits and pieces of section 9 of Turing's paper, in which he argues that, yeah, he basically didn't come up with this model by chance. His aim was to mathematicize what a mathematician is as a physical system, with using eyes and brain and pen and paper. This is where we were. Now, from there, we're going to leave these questions aside and we're going to develop the theory more today. But before I go, was there any questions about last time? Seems good. Okay, so we keep on developing the theory today. Sorry, I had a printer problem. Usually I manage to print the sketch of my notes, but not today, so I'll have to go back to my computer once in a while. First thing, a function f, which I write it down like this, has a starting set, if you want, onto a range B. Is partial I'm defining the word partial here if its domain of definition is not necessarily equal to A. Most of the time when we write a function f colon something arrow something else, the first something is the domain. But now I'm enlarging this because it might be useful to say, oh, you know what, A is a very nice set, like say all the natural numbers. But it might happen that my function is not defined on some specific natural numbers. And instead of breaking my head into pieces to find out what's the exact domain, I still write down A, but I say that f is a partial function. So don't expect f to be defined on all elements of A. So what that means, I'm just going to write down, there might be some little a and capital A for which f of A is undefined. Which is often denoted f of A equals that symbol here. Like basically a symbol which means forget about it. It's not defined.
I think someone called it bottom. Like, because if you flip it, it's going to be like top, and that's bottom. Just think of the lattice, then you have like top and the bottom.
Okay, cool. On LaTeX, it's \perp.
Perp.
Perpendicular. Yeah. It's just a notation. And some other notation, sometimes they say f of A up arrow like that. It's undefined. I don't know which one I'll use. We'll see. I guess the first one. Yeah, so by the way, by this definition, I said it might be undefined, so all the functions that we're used to, even if they're completely defined, they also qualify with that definition as being a partial function. But in general, it might be undefined. Now, when D equals A, we say that f is total. It's a total function. Okay, what I started to explain of what we did last time, but I realized I better not explain it because I'm about to do it now, is that we can see a Turing machine as computing a function. I briefly mentioned it last time, and here I'm going to be a bit more precise than what I did. So we can associate a partial function f sub t from 0, 1 star to 0, 1 star. By the way, or if you prefer from the natural to the natural, we have this implicit equivalence to each Turing machine.
Oh, are we recording?
Yes, we are.
Okay, cool.
Thank you for asking. To each Turing machine T. The input of T as the Turing machine, you know, like it had an input which was the initial segment of zeros and ones to the right of its head when the computation was starting. This is what we call the input of the Turing machine T. So the input of T is understood as the input of f of t. That's quite simple. ft. Yeah, so that's a Turing machine, and that's a function. It's like a mathematical thing. Well, that also, because we mathematize them, but you can think of them as an actual machine. Now the output is a little bit more tricky, and last time I was a bit hand-wavy. I said, yeah, what's residing on the tape is the output. And then one asked, oh, if there's blanks, does that count as a string? And I sort of left some problems under the carpet. We're going to address those problems now. If on input x, t halts, then the string of zeros and ones, so I'm excluding blanks, the string of zeros and ones that is being scanned and delimited by blanks defines the output of ft.
What does that is being scanned?
The head is still somewhere. After a computation, after the Turing machine halts, the tape will generically look like something like, there's infinitely many blanks on the left. I'm writing down the last two of them. And then there might be zeros and ones. Then there might be blank, 0, 1, 1, 1, 1. And there might be a blank, another blank, a 0, a blank, a 1, a 1, a blank, and infinitely many blanks to the right. We know there are infinitely many blanks to the left and to the right because it has only done a finite number of steps, and it started with infinitely many blanks on both directions. So it can only have affected a finite number of tape cells. Now, yeah, there was the awkward question of what is the output of a Turing machine in that context. And I think last time I said, well, you can just think of it as the first non-blank symbol. To the right of it extends a finite string. But yeah, that finite string contains blanks. It's a little bit awkward. It's like if all of a sudden we had a ternary alphabet. If I want to have a binary string, I have to select one of those string as being the output. And what I said here is that I want to have the one that is being scanned. So my computation is going to halt with the head somewhere, scanning some symbol when it halts. So suppose here it's hanging here. Well, then the output would be that string.
Oh.
Okay, it's surrounded by blanks. Eventually, we're sure that happens. It's going to be a finite string. That's my output. I mean, we have to make a choice. You know, there's plenty of choices to make once we define Turing machines. This is yet another one. But at least we're precise. we know there's a good prescription. So now we have an output for the function ft if on input x, t halts. You know, it's going to carry a computation, it's going to have a string residing there, and we can extract an output. However, this is the whole idea of having partial functions. If on input x, t does not halt, f of t of x is undefined. Well, equals perp or equals bottom. So now you see why partial functions are useful. Like, I don't know a priori how to specify the domain of a given Turing machine. There might be some inputs on which it doesn't halt, so it leaves a lot of holes in that set, which is the starting set, which is not necessarily the domain. The domain is, by definition, all of those x's for which the Turing machine halt, and then I have an output, which is going to be, yeah, that string. This defines ft of x in that case. Okay, so now we can move forward. A function f from the natural to the natural is computable if there exists a Turing machine T for which f equals f sub t. And that is a function equality. So it's not for some x, both functions are equal. They're equal as functions. They have the exact same input-output behavior. This is how we qualify a function to be computable. In words, is there a Turing machine that computes it, that does whatever the functional relation is? Okay, I should also just mention so that you know it, in the literature, if you find that word, also called recursive. So one could say it's a recursive function. I think it's a maybe older school nomenclature, but we still see it in some objects that we're going to see. We still use the word recursive, like recursively enumerable set. Some people are trying to fight and say, no, let's call them computationally enumerable sets. We're going to see what those are. But it's just that most people still use the word recursively enumerable set, so might as well tell you.
There was Gödel, I mean, he published after Turing.
Yeah, Gödel worked with general recursive function, which is yet another model of computation. Like we have briefly mentioned lambda calculus of Church. Gödel worked in developing the general recursive functions. I assume that's the origin of the word, indeed. But now that we know that all these models of computation are equivalent, I have not yet stated it, but now in 2023 we know that. Yeah, we sort of use those words exchangeably. It's a recursive set, it's a computable set, or it's a recursive function, it's a computable function. I also want to add that there's another word that is being used, but it is somewhat more loosely also called recursive. Yeah, then let's do a dot. And I should say the word effective is also used. As in, I would say, yeah, let's leave it like that. The word effective is also used, but not exactly in that sense. We don't say an effective function. We might read effectively computable function, but as an adjective, when in some loose way, sometimes the word effective has the meaning of, yeah, it's computable. The Turing machine would have been able to do that. I should say it's also used in some contexts so that your notes are clear. And by the way, we're going to use one such context. So again, I'm not, fighting to change all the words. There's something we'll see today. It's called an effective enumeration, and it's called like that. And so you know that effective has an illusion of computability. Okay, that's for words. Are there any questions?
I had a question actually about the output definition.
Yep.
Yeah, you mentioned it's a choice, but wouldn't the more natural choice be that you get the Turing machine to delete everything else, or just kind of erase the input and erase all the other kind of side work that it's done? Is there a particular reason for this choice, or
I don't think it's anything fundamental, no. Because if the Turing machine is about to halt, so suppose it's about to halt, it's gonna observe that, oh, there's no, in my list of rules, there's no more rules, I'm about to halt. You can always append it and say, please clean up your mess. And clean up your mess means save that string and delete all the rest. And in which case we would have what you would be more satisfied with. But yeah, there's plenty of those little possibilities to play with in definitions. Okay, we have seen computable functions, partial functions, total functions. Now the idea is we have partial computable functions and total computable functions. Okay, the function is computable if blah blah blah. It is partial computable or total computable if it is if f
It's both computable and partial or total.
yeah exactly I'll just say also partial or total respectively. It's a bit stating the obvious, but just so we're on the same page, we're going to have partial computable functions and total computable functions. A total computable function can be represented by a Turing machine, which is guaranteed to halt on all inputs. A partial computable function, it's represented by a Turing machine, which may not halt on some input. That's what that means. Yeah, and f is, as I mentioned, f is like partial by fiat. So one could say that a total computable function is also partial computable.
Yeah.
However, if we want to define more stuff, we could say it's not strictly partial, or, if you demand that something is strictly partial, if it's at least undefined on one input. But I'm not going to need that. Okay. Yes, when the context is clear.
Sorry, I have a question.
Sure.
I was wondering, how can we know if the Turing machine will halt?
You ask a hard question.
How can we know if it's computable or not?
That is a less hard question. When a function is computable, say I map the integer n to n squared. How can I know if it's computable?
Because it halted, right?
I just defined the function that there's no Turing machine yet. But it's a really good point to have a conversation about that. Like the function n maps to n squared. Intuitively, it's computable, right? Like in the intuitive sense, if you give me a number, I can spit out its square via some algorithm. So, but via this definition, which I erased, what does it mean to be computable?
It means that it exists an algorithm that determines it in a finite number of steps.
That is made a modern way of saying it, which I cannot agree more. It's exactly that. But what I wrote down here was that there exists a Turing machine. Yeah, an algorithm is good enough. So there exists a Turing machine, which when it's given n, a natural number, that's strange. No, our Turing machines were manipulating bit strings. Oh yeah, but it's fine because we know that natural number, they can be represented in bit strings. We've had this implied identification. So when it's given n, represented by a bit string, it can manipulate the bit string via a procedure, via a fixed list of rules, and halt with its head scanning a string, which again, by using the identification, I would understand as, oh yeah, that's n squared. I'm happy. If I find such an algorithm, then I'm done. I say, yeah, that function is computable. So this answers part of your second question. You also asked, how can I say if a function is uncomputable? We will meet some functions that we will be able to write down, and we will be able to verify, yep, it's not computable. But most uncomputable functions, I'm not even going to be able to write them down. So that's to be pursued. Your very first question was regarding, how do we know if a Turing machine halts on a given input? We will get into that problem eventually.
Okay.
Thanks for asking. It's called the halting problem. Okay, when the context is clear, we identify ft with t. Ft is the function, the mathematical function computed by t. T is the Turing machine, which is head. But sometimes it's just convenient to write f. So for example, we write t of x is the same as ft of x, where x is an input. Okay, so far we've seen computable functions, and they all have the form of functions of the natural to the natural, or the bit strings to the bit strings, and that might seem very constrained, like, oh yeah, I might be interested in functions that have a rational function, or have, I don't know, they eat a graph as input, or function over other things than just natural numbers. Although the set of functions n to n seems restricted, via suitable encoding. Of other discrete sets. Into n. The computable functions may be viewed as computing other functions. Well, sorry. Other kinds of function. Other kinds of functions of of a countable set into another. Right, so we have functions which are from the natural to the natural. It seems fun if what we want to do is arithmetic, but usually we want to compute other things like, I don't know, properties on graphs. Is this graph tree-colorable? If the answer is yes, I will map it to a 1. If the answer is no, I'll map it to a 0. So I could see that as a function from a graph, eating a description of a graph, into a bit, yes or no. Well, then don't worry, there's enough power into that, because we just understand that the domain, yes, it's going to be understood as a natural number or as a string, but that string encodes in some canonical way the graph. And the answer in my example, the answer is just 0 or 1, yes or no. But that was just one example, and in fact, we're going to do another one which is quite important right now. And it's to naturally extend functions of more than one arguments. So we only have functions from the natural to the natural that are defined by Turing machines. Yes, again, okay, but a pair of natural numbers is also a discrete set, which could be put into correspondence with the natural numbers. So I could have computable functions which take as input a pair of arguments and produce, one output out of those pair of arguments. Yeah, example. A function G, I gave it a name, natural to natural to natural into the natural. So I'm extending the starting set, which maps, so you have x1, x2, xn, and it maps it to, well, g of all of them. Well, if that function is computable, it can be viewed, a function g can be viewed as being computed by a Turing machine expecting an input of the form. We have seen some encodings of all of these into one single natural number. And one of them was, for example, x bar 1, x bar 2, x bar n. So there is a Turing machine which, the way it's done, will expect an input which is only one single string, but that string encodes the n strings or the n natural numbers. And then I don't know, if that function is multiply them all, it will read its input, it will understand what it means, it will store them or it will manipulate them in order to halt and compute, in my example, the product of all those inputs.
Sorry, x bar was a bunch of ones and then a 0 and then the bit string of the number? Like
Yeah,
the ones,
x bar was equal to 1 to the length of x, 0, x.
and then how does it know when the number is finished? Like how does it, if it's just reading x1 bar, x2 bar, xn bar, how does it know that xn bar is the last one? Instead of like, sorry?
We code in it with a prefix code.
You start reading
Yeah.
you read the first ones. So you
I
got
know, but if it's a prefix code, then like,
Okay.
my question isn't so well phrased, but like,
I
if
understand
it's
what
just
you
getting
mean.
a ton of bits, how does it know that I'm supposed to read n numbers and not n plus 1 numbers?
Oh,
If there's
okay.
more bits in the
Yeah.
string, like how does it decide? I mean, you could encode it, I guess, that you could do like,
Yeah.
the first thing is, like you basically put a bar over the whole thing and you say, there's gonna be n numbers coming, and then each one of them.
That's one solution. I have 3 solutions for you. One thing is to say that G implicitly knows in advance n. It knows it's expecting 17 inputs.
Okay.
G is a multiplier of 17 numbers, for example. So if it implicitly know n, it's like embedded in its internal states and so on. It's not like a generic multiplier. That would be an easy solution. Another solution which a bit cheats is that suppose it doesn't know n, but it will eventually hit a blank and it will know that that's the n.
Okay.
That's also not very satisfactory. But if you want to have like a generic multiplier, you could also give n bar as your first input.
Okay.
So then it knows how many numbers to look for in his memory, and then it's gonna check all of them. And then it doesn't overshoot into a blank. This would be a completely self-delimiting encoding of what I call the generic multiplier. I made that name up just to mean it multiplies an arbitrary number of numbers. It's good that you start thinking like that, because these are going to be, for the purpose of computability theory and Turing machines, it's not super important. But once we get into algorithmic information theory, and we have to be precise with prefix codes, and this is the kind of thing that might come up as an issue. Like, if your Turing machine is implicitly using a blank as extra information, then the size of the program is not exactly as it's not the same measure of program size that if you write down a Turing machine which does not cheat by reading a blank when it overshoots. We push that for later. Okay. So we saw that computable functions, despite the fact that they are of the form n to n, or bit strings to bit strings, they can compute, any functions of discrete sets into other discrete sets, basically. Countable sets into countable sets. Now, just by curiosity, how many such functions there are? Functions of a countable set to a countable set.
Bijection or function?
I guess a bijection would be a subset, but in both cases it's the same answer.
Actually, uncountable.
It's uncountable. Correct, it's uncountable. There's uncountably many functions of the form natural numbers to natural numbers. How many Turing machines there are? Countable. I mentioned it last time. Turing wrote it on page 1 of his paper, which we read together. I sort of gave a hand-wavy argument. After the break, we're going to see that there are countably many Turing machines. And not only there are countably many Turing machines, but we can order them in a very specific way, which is going to be useful for later on. So right away, by that argument, we know that they are uncomputable functions. Right away. There are much, much, much more functions like that than they are Turing machines.
Is there a canonical example of one?
Sorry?
What's a canonical example of one?
Maybe Thursday if I'm fast enough. Otherwise, next Tuesday. Have a nice break and meet you in 15 minutes. Okay, let's continue. I told you, well, yeah, we finished saying that there are countably many Turing machines. We can put them in correspondence with the natural numbers. There is, and now I'm using the word effective enumeration of Turing machines. Of all Turing machines.
Sorry, effective was computable?
I would like to say yes, but in most cases in which I see the word effective, it's related to computability. So we will see the precise meaning of effective eventually. And you say like, oh yeah, okay, it's really like computable. However, we can just not interchange it with like effective function. That's not a thing. It's a computable function, a recursive function. Computable as an adjective would qualify computability, recursive also. Now effective is, in my understanding of things, and I'd like to be error corrected on it because I feel like it's a bit shaky, but every time I read effective is like, it's linked to computability, but slightly by a slight detour. In what follows, I will be able to make precise what I mean by effective enumeration of Turing machines. For now, just think of the word enumeration as T1, T2, ... And all Turing machines are in that list, are in that enumeration. So I'm about to basically prove that there is an effective enumeration of Turing machines. I'm gonna show an enumeration, and at the end we're gonna retrospect and we're gonna say, oh yeah, it's effective in that sense. I'll make that clear. So as a first step, the list of rules of Turing machines can be encoded in a string. That's the first thing to remark. So a Turing machine was defined by its list of rules, and we can encode that in a string. So right away, if we take this for granted so far, we see that there's countably many Turing machines, because there's countably many strings, and I can embed the Turing machines into the strings. Now let me be more precise. Each rule has the form Q, S, A, Q prime. The two first arguments were the start configuration. So the machine was in the state Q. It was scanning the symbol S. And then the next two things were encoding what it does. A was an action. Either write a 0, write a 1, write a blank, move left or move right. And Q prime it's going to be its after state that I call. After the small operation, it's going to get into state Q prime. So the rule have the form like that. And from there we can, fixing and encoding, I'll fix an encoding of that alphabet into S bits. and the encoding is called E. So what do I want to do? These guys, these symbols, they all take the form either of a Q, an internal state, or of one of those five. 0, 1, 2, 3, no, 0, 1, BLR. So I'm going to say, I'm going to encode this into S bits. I need S to be large enough. What is large enough? Well, if I have N bits, I can distinguish 2 to the N different symbols by a fixed length encoding. So I need S to be the ceiling of the log of the number of internal states plus 5. I'm sort of reverse engineering this here. If I want to encode 2 to the N symbols, I need N bits. Now, in general, the number of symbols, which is the cardinality of Q plus 5, is not going to be a power of 2. But I just round up that. Okay, if I have 100 possible internal states plus 5 other symbols, then the next power of 2 will be 128, and the log of that will be 7. Thank you. So I encode that in 7 bits. Okay, it's details, but you know it can be done. So by fixing and encoding E, each rule can be encoded as a rule was having that form. It was a quadruple. So my encoding would be E of Q, E of S, E of A, and E of Q prime. Now I'm still doing point 1. What I want to do is encode the list of rules of a Turing machine into a string. Right now what I have done is I found a way to encode one given rule into 4 S bits. S bits here, S bits here, S bits here, S bits here. But I'm going to have some number of rules to encode. Let R be that number. Okay, observe that R is smaller or equal than 3 times the size of Q. Why? Because a rule basically tells you what to do once you are in state Q and you scan symbol S. And as we mentioned, the machine is deterministic, so I don't want to have 2 rules with the same first 2 entries. So I have at most as many rules as I have pairs of 2 entries, of the first 2 entries, which is Q, well, cardinality of Q times 3, because there's 3 possible symbols to being scanned. So there's at most as many rules as, I'm in state 1 and I read 0, I'm in state 1 and I read 1, I'm in state 1 and I read blank. I'm in state 2 and I read 0, I'm in state 2 and that's 3 times cardinality. So the list of rules of T, I gave it a name all of a sudden. I said Turing machines, I'd say let me write maybe in red. So You see my correction of a Turing machine T. I'm just choosing a given one. The list of rules of T can be encoded as okay, so these are going to be each individual rule, but for my encoding to have sense, my Turing machine, well, my encoding needs to specify what's S and what's R, the number of rules. So I'm just going to do S bar, R bar, and then I go E of Q1, S1, A1, Q prime 1. No. There's E all over the place. Sorry, my E is encoding one specific symbol here. E of Q1, E of S1, E of A1, E of Q prime 1, E of Q2, E of S2, E of A2, E of Q prime 2, E of QR, E of SR, E of AR, and E of Q prime R. There's our rules. Each rule takes the form of a quadruple. And here I'm encoding each element of the quadruple one next to another. Now I prefix this with S bar. So once you read the encoding, you decode S bar first. So you know what's S, which gives you the information of each of these pieces have S bits. Each of these pieces have S bits. And you read R bar, which tells you how many rules there are. So with S bar and R bar, you can know how many bits you have to look for, and you can decode it appropriately.
So here by bar, you just mean the size of the thing?
No, bar is always the same. I reserve the bar for, again, X bar is equal 1 to the length of X, 0, X. It's a self-delimiting encoding of X. So when you read X bar like this from left to right, you know what's X without overshooting.
So so it's like the length of a number. X bar, like R is a number, so R bar is the length of a number in the number itself.
Yes, this means 1, 1, 1, some number of times. And that number is the length of X.
Okay, for a second I thought you would just like put ones for the number of rules that you have, but you have this kind of nested encoding, the length of the string and then the string itself.
Yeah. Well, so when you see S bar written down like that, you don't really have to expand it in your mind. You can just say, oh yeah, that's a self-delimiting encoding of S bar into bits, which means that a Turing machine could read that and say, okay, yeah, S is, I got it. And then, oh, R is, okay, I got it. The Turing machine is going to be a mess to actually program the Turing machine. Nobody ever programs Turing machine, but you know that there would be an algorithm which would say, count the number of ones. This tells you the length of the string you're about to read, because then you hit a 0. And after that 0, you have that length, and this is going to encode you S.
It's a dynamic bootloader for it.
Yeah, okay. And then R, and then since you have the information of S and R, you're good, because you can get all those rules. You know that these E, they're just stick one next to another, but you understand that they come into bits of 4. It's a string. You encode the list of rules into a string. Maybe I should just add the list of rules encodes all that there is to know about T. I should expand a bit on that, because once we saw Turing machines, I told you, yeah, Turing machine is defined by a tape, a set of states, and rules, and so on. But you can see that the rules embed everything. They embed what is the set of states. You know, if you really deploy the list of quadruples and you write it down in your notebook, you're going to be able to say, okay, yeah, there's everything I need to know about the Turing machine. I know what's its set of states, and maybe one thing that should be mentioned is that it needs a initial state. I mentioned that last time. A Turing machine needs to be in an initial state. But by convention, you can say that the first state that you will encounter in the first rule is your initial state. That's like a canonical way of distinguishing your initial state. So I'm going to just write this as a big encoding of the Turing machine T. In fact, it's an encoding of its list of rules, but as I argued, all that there is to know about T is encoded in its rules. So this was point one. That we encode the list of rules in a Turing machine. The list of rules of a Turing machine T can be encoded into a bit string, large bit string. That's one part. But what we want is an effective enumeration. We want to say that's my first Turing machine, that's my second Turing machine, that's my third Turing machine, and so on. So what we can do is take all Turing machines and all their encodings into bit strings. That will give a subset of all bit strings. Then I can lexicographically order them. And now that I have a lexicographical ordering, I can say, oh, that's my first Turing machine. That's my second Turing machine. That's my third Turing machine. And so on. I'll have T1, T2, T3, and so on. So I write here point 2. All bit string that correspond to a valid encoding of some Turing machine are listed in lexicographical order, or are ordered lexicographically. You realize right now that most strings, they just don't qualify. You know, they start with 0, 0, 0. You're done. If it starts with 0, 0, 0, it doesn't work. Because you're expecting some S bar. S bar needs to start with some ones. If it starts with a 0, it tells you that the string you're trying to encode is the empty word. Why? What's epsilon bar? Well, it's 1 to the length of epsilon, 0, epsilon. 1 to the 0, so you encode 0 times a 1, you just have 0. Okay, cool. So if I read a 0 here, I understand that S is equal to the empty word. which I needed to encode a number. The empty word was my first number. So S is equal to 1. Which is a very bad sign because it cannot even qualify. S is supposed to be the ceiling of the log of some number plus 5. So it doesn't work. So all this to say that if your string starts with a 0, it's not a valid encoding. All this to say that most strings are not valid encodings. But that doesn't matter. What I do is I take all valid encodings and then I lexicographically order them. Okay, and therefore, the index I or Gödel number, it's also called this way sometimes, of each Turing machine T. No. Sorry.
Is its position in this list?
Yeah, exactly.
So
The index I assigned to a Turing machine T excuse me again, the index I or Gödel number I. So index is one name for it, Gödel number is another name for it. I is assigned to a Turing machine T if E of T is the ith element in the lexicographic order of Turing machine codes. Okay, so as I said, you can order all the possible codes lexicographically, and then I say the 1, the 2nd, the 3rd, the 4th, and in general the ith. And the ith to the ith will correspond some encoding of some Turing machine T. Or if I want it the other way around, if I give you a Turing machine T, you will find what is its list, what is its encoding, sorry. And you will also generate all the encodings of all Turing machines, and you can find, oh yeah, it's the number I. In fact, I'm already giving you some form of algorithm to be there. So far, and this will be the notion of effective. It's like that the enumeration is not only done, there exists some enumeration, but there is a notion of an algorithm can generate the 17th Turing machine or the 176th Turing machine and so on. I'll be back to that in a second.
So what Vol's, sorry, go ahead.
No, go.
So Vol's question earlier is related to the sparsity of this encoding.
Yes.
That
correct.
basically, if you give me a Turing machine, I can compute its encoding, E of T, but then to know which index E of T has on my list of all Turing machines, I need to compute, if it's number 17, I would need to compute up to the 17th. And if you have a really sparse list where most of them don't correspond to a Turing machine, you could be computing for 10,000 years until you get to the number 17.
You could. Yeah. Notice that I have not tried to be economical in my E of t.
Yeah.
Like, for example, I encode with many bits something that I know is only 3 symbols. You know, like the second entry is just a 0 or 1 or a blank. You could make the case to try and compress the encoding E of t, but it won't matter for our purposes.
Also, the list of rules, the permutation of it doesn't matter, right? So, like, we should make sure that, like, we have some sort of ordering of rules. And do we also differentiate between functionally different Turing machines? Because I could relabel states based on however I want to name them, and like I could kind of reduce them.
Okay, regarding your first comment, yeah, the ordering of the rules does not matter,
Yeah.
except for, I only mentioned it orally, but I didn't write it, that we sort of single out the initial state by being the first state encountered in the first rule. That's one thing. And then functionally different Turing machines, you might run into a hard problem. It's in general undecidable to say if 2 Turing machines are doing the same thing.
Can I ask a question?
Sure.
Did you say that there is an algorithm that provided a number, let's say 3, returns the third Turing machine?
I'm about to actually, I was going ahead of myself.
Yes, but so there is a Turing machine that does it. There is a Turing machine that returns for instance, the third Turing machine, so it's also among the list. I don't know if this is my question.
I see where you're going with
Okay.
this. Yeah.
Can you repeat, please?
I mean, if there is an algorithm that takes as input, for instance, number 3 and returns the third Turing machine, my guess is that there is also a Turing machine that computes this algorithm in some sense.
Ah.
So it's supposed to be in the list.
Yes. You are finding something very special. You're finding the universal Turing machine.
Ah, okay.
Well done. Okay, so I mentioned here that for a Turing machine T, its index I is assigned to the rank of E of T, if you will, in the lexicographic order of all Turing machine codes. Now, this yields an enumeration of all Turing machines. T1, T2, T3, and so on. I'm going to go back on the higher board to come back to the notion of effective. I'm going to define what I mean by that, what is meant by that. And again, it's in most textbooks, it's really called an effective enumeration of Turing machines. So I'm not trying to fight and say, oh, we should call it a computable enumeration of Turing machines. Let's just call it like that. Okay, remark. It is effective in the sense that one can construct a Turing machine M which on input I returns E of Ti. It returns the encoding of the rules of the machine Ti. I would actually like to tell you on input I it returns you Ti, but a Turing machine needs to return a string, so the best it can do is return an encoding of that machine Ti. And here is M. Here is what M does. On input, what's the input? I.
It starts constructing all the Turing machines. It starts checking all strings,
Yeah.
constructing all Turing machines until it runs into the I.
Yeah, it's gonna temporarily ignore the input.
Yeah.
And it's gonna check for each Y in 0, 1 star. Lexicographically. So in lexicographic order. Check if Y corresponds to E of T. For some T. I erased that part, but you know we had E of T was equal to S bar, R bar, E of Q1, E of S1, E of QR, E of SR, E of AR, E of Q prime R. It's highly constrained, but all those constraints can be checked algorithmically or by a Turing machine. So it's gonna start with the empty string. It's gonna say, haha, you don't qualify. It's gonna go on to 0, haha, you don't qualify. Eventually it's gonna get into some more interesting strings. It's going to verify if the syntax is correct. Is it encoded S, R followed by 4 times R strings of length S and so on. It's also going to verify if the rules are correct, namely if it's a deterministic machine. I have a list of rules. It's going to check to make sure that for each first 2 entries, there's only one corresponding behavior, one corresponding output. Otherwise, it's just going to reject. It's going to go to the next Y. Check if Y corresponds to a valid encoding of some Turing machine. If it does, increment a counter. Add 1 to a counter. I call my counter S. So S starts at 0. If I find a Y that corresponds to some encoding, I add 1 to S. And when S equals Y, output Y, which will be at that stage E of T. E of T of I. It will have found the ith Turing machine in the lexicographic ordering of all encodings of Turing machines. I'll just try and continue a little longer because we're getting to, I guess, a new section, but an interesting one. The universal Turing machine. There are countably many Turing machines. But one of them can simulate them all. A universal Turing machine U is a machine which expects an encoding of a pair I, X. It obviously, the input of the universal Turing machine is going to be a bit string, like all Turing machines. But as we said, we could think of those as a bit string might encode various bit strings. In this case, the universal Turing machine expects a bit string which encodes a pair. And this pair is IX. And what it will do, it will simulate the machine Ti on input X. Therefore, U of, it encodes a pair, so I'm going to encode it like that. I, X is equal to T sub I, the ith Turing machine, on input X. And this holds for all I and for all X. So that is the function, if you want, calculated by the universal Turing machine is that function here. So where we're going is, I've defined it, and as a central result of computability theory is that a universal Turing machine exists and can be constructed effectively. M does a big part of the job, right? Because M tells you on input I, how can you find the list of rules of Ti? going a little further, and actually I'm not going to program the Turing machine into the details, but we could see that, oh yeah, the universal Turing machine will simulate TI because it will save on its state the rules. So instead of looking into its own rules, what to do if I'm in state Q and I scan symbol 0, it will look into this table that it has generated from I. Questions? Cool. I wish you a fantastic Tuesday.